Okay, the third part of the chapter is about the goodness of fit, but with a particular probability. And in this case, a Poisson distribution probability. So we are going to have the observed values, and we are going to say, is this observed data come from a Poisson distribution? That's it. That's the purpose of the goodness of fit for the Poisson distribution. It's important to note that we are going the Poisson distribution. You already know this, but let me tell you, the Poisson distribution is pretty much used for QM theory, where we have the number of customers every hour or every particular period of time. And the opposite is the exponential distribution, where you have the number of minutes between arrivals. Anyways, this is for the Poisson distribution, and the important part is that you need to have at least 5 elements in the expected category. So we have different categories. This is the number of customers, 0, 1, 2, 3, 4, and 5. And this is the expected. We need to have at least 5 in the expected. We have the observed, or the values that actually happen. And what we are going to do is exactly the same. We are going to have the summation for each one of the categories. Frequency minus expected squared divided by expected, and we are going to compare with a high square. This is a high square, and this is alpha. How many degrees of freedom? Well, in this case, we have the number of categories at the end is k minus 1, but since we are going to estimate the mean or the mu of the Poisson distribution, we have to delete that also, because every time that we estimate the population parameter, we have, the process loses 1 degree of freedom. So in this case, since for the Poisson distribution, we need to estimate the only parameter for the Poisson distribution is mu. So we have to estimate 1 parameter, so it's k minus 2, where k is the number of categories that we have over here. So we're going to have a high square with k minus 2 degrees of freedom, and we are going to have this test, and we are going to compare this test value with my critical value, and this is rejection zone, and this is the not rejection zone. Again, for this one, we are going to have only the upper tail test, because we have the null hypothesis that it fits, and the alternative, it doesn't fit. What? The Poisson distribution with the mu that we calculate or estimate, if you will. Okay, let's do one problem, one example. And again, this is tedious, but it's not difficult at all. Okay, let's do problem number 23. On your book. It says the number of incoming phone calls at a company switching board in 1 minute interval is believed to have a Poisson distribution. Use alpha equal to 0.1, alpha equal to 0.1, and the following data to test the assumption that incoming phone calls follow a Poisson distribution. So, and they give us this number of incoming calls, number of calls, and we do have the observed frequency, and they gave us 0, 1, 2, 3, 4, 5, and 6, right? Yeah. And we have for this frequency 15 times it didn't come through any call. 15 times. 31, only one in that minute. 20 when we have 2 calls in 1 minute. 15, 13, 4, and 2. Okay. So we have a total of 100 periods. Number of periods of 1 minute that we have data from. Okay? And we do have that in those 100 frequency, we receive 0, 15 times, 1, 31 times, 2 calls, 20 times, 3 calls, 15 times, 4 calls in that minute, 13 times, 5, 4 times, and 6, 2 times. Okay, so we need to know how many calls we received total. Okay, in order to do that, we need to multiply the number of frequency times the number of calls to see how many total calls, not how many periods, how many total calls we received in the 100 periods. Okay, so this is 0, 0 times 15 is 0, 31 times 1 is 31, 20 times 2 is 40, 15 times 3 is 45, 13 times 4 is what? 52, 4 times 5 is 20, and 6 times 2 is 12. If we add this number, this is the total number of calls that we received in the 100 periods, 1 minute periods. And this is equal to 200 calls. Okay, so we receive a total of 200 calls in 100 1 minute periods. Now, we need to estimate the mean or the mean number of, and the mu, remember, for the Poisson distribution tells you the number of calls of the average calls that you receive in your time period. In order to do that, we need to know how many calls and how many periods. So in this case, your mu has to be equal to 200 divided by 100, and you have an average of 2 calls per minute. And this is the assumption that the mean of the distribution is equal to 2. So we are trying to calculate what is the real mean of these distributions. Since we are going to tell that this is the Poisson distribution, we need to estimate the mu. So this is my point estimate of the mu. Now that we have the mu, then we need to have the probabilities, right? And the probabilities come from the Poisson distribution, and you need to have the Poisson distribution, and this is on page 991. Those are the Poisson probabilities, and you look for the mu is equal to 2, and that is on page 999 on the middle. So you look for mu is equal to 2 over here, because that is the estimation of the parameter. In other examples, it could be different than 2. For these cases, 2. So we're going to have these probabilities over here. For 0, I would have, what, 13.1353. The next one is 0.2707. The next one too is 0.707, 0.1804, 0.0902. For 5 is 0.0361, and for 6 is, well, what happens? We have 6, 7, 8, and 9. What we are going to do is what? For the 6 or more, let's put it in here, 6 or more. And for the 6 or more, I have what? 0.012 plus 0.0034 plus 0.0009 plus 0.002, 0.0002. And that is equal to 0.0165. Okay? Now, with this value, I'm going to calculate the expected value. Remember that we need the expected. We have the frequency, but we need to have the expected. In order to calculate the expected, we need to calculate the mean. From the mean, we extract the probabilities from the Poisson distribution table, and basically what we're going to do. So what is the expected? A very common error that people do is that they take the total calls times this probability. Is not. You have to take the total number of periods. So you are going to have 100 times 0.1353, and it's 13.53. Okay? And 27.07, this is the expected value for each one of the categories. This is the categories. So for this one is 2707, 18.04. Why? Because we're saying that 100 times 0.8004 is 18.04. 9.02, 3.61, and 1.65. Okay. Now, remember that I told you that the expected cannot be less than 5. And we have two categories that the number, these categories are less than 5. So what we are going to do is to take these two categories and grab it into one category and saying 5 or more. This category over here, we are going to have this category with 5 or more, and we are going just to add this element, 5.26. In order for what to have, the expected in any category shouldn't be less than 5. That's one of the requirements. And we are going to compare with the chi-square. Now we know how many categories we have already. Alpha is 0.1, and the number of categories, we have how many categories? 1, 2, 3, 4, 5, 6, because we ended up with this one. 6 categories, okay, is equal to 6. Minus 1, because it's minus 1, minus another one, that is the estimation of the parameter. So it has to be k minus 2. So the degrees of freedom in this case has to be equal to 4. And go to the chi-square probability distribution, and we will have 4 degrees of freedom. 0.1 is 7.779. Okay? Now, test that we're going to do. The null hypothesis says it fits this Poisson distribution with mu is equal to 2, and the alternative hypothesis, it says that this data doesn't fit, or do not fit this distribution. So what we're going to do is what? Do exactly the same, frequency minus expected, the square divided by expected, and add them all. And that's it. I mean, the frequencies is, let's start with the number of calls equal to 0 is 15 minus the expected, 13.53, square divided by 13.53, plus the next category, number 1, frequency, 31 minus 27.07 squared divided by 27.07 plus the next one, 20 minus 27.07 squared divided by 27.07 plus the following category, 3, 4, and 5 or more. Okay, and this is my test value, and that is equal, I repeat it, is what it says, 4.95. Okay, where is my 4.95 in here? Over here. So we do not reject the null hypothesis. So we have evidence that says that this, we don't have evidence to reject that this is a Poisson distribution with mean equal to 2. So we failed to reject the null hypothesis, so we failed to reject that this is a Poisson, this is not a Poisson distribution. So it may be that this is a Poisson distribution. So we do not reject the null hypothesis. And again, the null hypothesis is said that it fits the Poisson distribution, and the alternative, it doesn't fit the Poisson distribution. So we fail to reject, we do not reject the null hypothesis, so it may be that it fits a Poisson distribution. That's it, basically. So it's complicated. It's not complicated. It's hard to do the calculation, but it's not that complicated.